And everybody can hear on the Zoom, I take it. So, all right. Good. All right. Well, good morning, everybody. Good to be back here. I spoke at the last summer school a couple of years ago. So apparently that wasn't totally terrible because I got invited back. So you can at least have a minimum bar on your expectations. Yes, and I do run TACC. And I think for those of you who are here in person, you got to visit last night, is my understanding. So I was out at Los Alamos National Lab. So therefore, I stole a couple of their slides for this talk with some flights where I spent 2 hours sitting on a tarmac waiting for a mechanic to figure out how to fill out a form. So got home sometime after midnight last night. So this may be slightly disjointed. But I'll say a few words about TACC for those of you who didn't get to go to the visit who are online. And then I want to talk about a few trends going on in high performance computing. One is sort of what appears to be the general slowing of performance gains. I'm going to say a thing or two about quantum because something just dropped off. There it goes. I'll say a thing or two about quantum because I actually have some reason for optimism that especially for the kinds of systems you work on, there might be useful quantum computers. And you guys are mostly young, so you'll see them, even if we don't. And then talk a little bit about the role of AI in science, because AI is warping the HPC industry at a very rapid rate, and it's going to affect everything we do. Moving on. So mostly talking about sort of what's going on and less, well, I suppose if you hate computing, it's quasi-technical, but not super deep technical stuff. Again, you got to come up and see the systems last night, but we run big platforms, mostly for the National Science Foundation. Some are funded by here at UT, a few by other sources. We do work with a lot of agencies, but NSF more than any others. In fact, my other mad scramble this morning was doing the $12,000 revision they asked me to do on the $459,772,000 budget for the LCCF, because if that was off by 12,000, well, you might be engineers, you understand significant figures, right? So the anyway, but we're about to start operating this leadership facility. Stampede 2, we have just decommissioned. You probably saw its remnants yesterday. There's Frontera, which is our big current production platform. We have a whole bunch, but basically what we do at TACC, and at this point this year, we just went over 200 staff that we have at the center now, 4 of whom I think you met last night. But we provide hardware, computing, data, AI capabilities, and platforms for that. All right. See, normally I do my own technical difficulties. I run this computing center thing. So yes, they were amazed to find out I could work a projector at Los Alamos yesterday. But so obviously the platforms are huge. But I think perhaps even more important, even if we had much smaller platforms or we were using outsourced platforms somewhere, we have the expert help to be able to use it. And increasingly, we try and provide it in the ways that you want to consume it. I think you've been using some of our systems. I think mostly just directly logging in this week, right? But Jupyter is coming over the weekend or something. So, but yeah, whether it's a web access or direct command line access or real time or through an API, coming up with the ways that you want to consume computing. And we found that that's sort of increasingly, especially with cheap digital data everywhere, has become ubiquitous, not just across the sciences, but across pretty much every department at the university, where in some way or another, they need increasingly large platforms to manage data or do their large language models, which is driving us. So, fundamentally at TACC, our job is to enable any kind of computing that doesn't fit on your laptop anymore. So once you go past the laptop scale, that's where we would like to work with you. Yeah, that one is going to eat about half the Frontera nodes next week for the latest version, but that's tornado simulations from Lee Orf at Wisconsin. Those runs take about 200,000 cores. So actually, I think you've been on Stampede this week because we had Frontera offline for 3 days to do full system runs for a few people. So, which means 200 to 400,000 cores. So I actually pulled my slides from 2 years ago and realized the systems keep evolving. So I killed a couple, crossed some out. You saw that we're under a fair amount of construction when you were there last night, I suspect, because we have platforms coming in and out, right? Frontera is old by supercomputing standards, but it's still our biggest and most capable platform right now. But it was deployed in 2019. And so if you have a laptop from 2019, you're probably frustrated with it and ready to throw it at the wall, and found out that none of the plugs work because we changed to USB-C and everything, right? So supercomputers sort of age in the same way. It's just more depressing because they cost a lot more, right? So Frontera depreciates at about $1 million a month. But it was the number 5 machine in the world when we started back in 2019. It's still around 30. And we'll probably run it into the first half of 26 because that's when the replacement will be up and running. If all goes even halfway well. You know, you saw the remnants of Stampede 2. That's when we shut down, ended production in January, have pulled it apart, and in its place, you might have seen parts of Stampede 3, which just hit production in May, which is still a largely Intel-based system, but where we've added high bandwidth memory. So if your algorithms are bound by how fast you can fetch from memory, we've seen for a lot of codes, that's a 60 or 70% performance boost just from the memory bandwidth change. One thing I'll talk about later is the peak floating point is not going up at the way it used to be. This gives us the opportunity to go balance the systems better. So we're seeing, you know, so these have roughly triple the peak of the nodes you've been running on the old Stampede 2 Skylake nodes. But we have applications that do 5 times better than they did, even, which is, you know, higher than the difference in peak performance because we can raise the efficiency with high bandwidth memory. Lone Star 6 was the one you saw immersed in mineral oil. Is our a lot of GPUs in that one, so a lot of AI, but our AMD-based platform. Vista was the one you saw getting installed right now. Is our latest all NVIDIA system. So another trend there, moving away from x86. All the CPUs in there are ARM-based, and so. And it's actually the bridge system for what will likely be in Horizon, our next big one. But that's the brand new one. We have cloud systems like Jetstream, Chameleon 4. Just Chameleon is our cloud testbed system where you can tear it apart and experiment with composable hardware or various different things. It's more of a CS testbed. That one, I might have jumped the gun. I think we're getting the cooperative agreement next week on that, but is about to be awarded through 2028. We have a whole bunch of storage platforms. You probably saw Corral and Stockyard Ranches in our other data center because that's our backup system. So you don't want to put it on the same floor with the stuff that it backs up. But yeah, we have 75, 80 petaflops. We have about 16,000 servers that we run. We have a little over 1/3 of an exabyte of data at this point, and growing pretty quickly. And all of those numbers will go up dramatically at the end of next year. So this is just sort of the curve we've been on. I'm going to show you the overall industry curves, which look nothing like this, because some of this comes from technology. And this is top system performance for our single biggest platform at TACC, 2001 through Frontera, which is about 40 petaflops. And we were at, you know, and this is in teraflops. So we were at half a teraflop in 2001. And now we're, what, 80,000 times faster than we were by 2019. The end of next year, we should hit a machine at 400 petaflops. So we'll be 800,000 times faster than we were 20 years ago. And yet, what is this called? I just figured this out a few days ago, but in economics, this is called Javon's paradox, right? That the more capability we have, the more demand there is. It's about induced demand as you make stuff easier to use. But and now we're seeing that with AI, right? The more computing we have, the more demand for computing we seem to have. So we're still about 5x oversubscribed in terms of what we can deliver versus what's out there. Is that zoom bar in the way? Let me see if I can move the controls, or just do that. There we go. Yeah, so we've been on this upward curve, and some of this is technology, which I'll talk about in a second. Some of this is funding and success, because our current systems are much more expensive than our old systems. And that is a bit of a problem for sustaining this, but we've been able to deliver a lot more performance over time. So yeah, so let me talk about sort of three things going on in industry. And I want to spend most of the time probably on AI related stuff because, like I said, it impacts everything that we're going to do, not just AI, including impacting this curve. So this one's a little complicated. And sorry for the stolen image of someone else's slide. There's a few of those. But this is from the International Supercomputing Conference just last month in Germany. And as you can guess from this fine phone camera image, I was actually sitting in the audience at it. And what this shows is, so starting in about 1998, well, or 1988 rather, and the list started in 1989, where we started tracking the top 500 based on a single benchmark that gets run that solves a big system of linear equations. You can scale up the system size, so it's always been scalable for top 500 performance. And for the first 30 plus years of the list, we were getting about a factor of 1,000 every decade, give or take. So 11 years really. So what this chart measures is if you add up all the systems that are ranked in the top 500 in the world, and then you look at the multiple from where you were 11 years ago, this was the average performance improvement, right? So you see in 2004, which would sum everything back to 1993, we were 600-700 times faster than we were in 1993. This sort of peaked in 2012, 2013 at about 1,200 times improvement over 11 years. And then since 2013, something presumably bad has happened, right? So I just actually threw this chart out to my staff at a staff meeting about a month ago and said, everybody come think about this and we'll talk about it next time as to what has gone on here. And there's actually a few things that have gone on here, some bad, some not so bad, because like any graph, it can be carefully manipulated. And so there's some economics and crazy stuff, and then there's some technical stuff that has led to this dramatic tail off. But let's just talk about this for a few minutes. So especially if you work in computing, what the conclusion everybody jumps to when you see a chart like this and it's plummeting is it's the end of Moore's law, which, by the way, has been forecast for every year since 1986, I believe. So, and it actually still hasn't ended. And although, I just pointed out that everyone in the last 40 years has been wrong with this forecasting the end of it, but we're really close to the end of it. And that's because in the current silicon process, we're at 10 atoms across for transistor features. And when one atom moving can destroy your transistor performance, that's getting serious, right? So, and I have serious doubts that we're going to go below one atom per feature. So we got to be near the end, right? So unless you figure out a way for us to do this at the subatomic level. But Moore's law anyway has never meant what people thought it meant, because the rough estimate was that every 2 years performance would double, or every 18 months. He keeps changing the constant, which is good for a law. But yeah, so Gordon Moore, who was the original CEO at Intel, but also founded Fairchild and did a lot of stuff. But in 1965, he just made an observation. All he did was look at past data, make an observation, get a law named after you. So important things to remember for your career is that looking back and projecting forward, that the number of transistors we can fit per unit area was going to double. And things get smaller, and smaller has been traditionally better, not anymore, in silicon. So this would just keep on going. He said every year, but in 1975, he's like, okay, we've sort of hit the peak of every year. Let's call it every 2 years. So you can be wrong and adjust, still get forecasts, foreshadowing modern politics. But it's become known as a law. And everybody equates it with performance, but it really says how many transistors we can fit in a given area is what changes. And that actually hasn't changed. So very often it gets confused with Dennard scaling, which is what ended in 2005 and started this horrible trend, which said that as transistors get smaller, right, so we're putting twice as many in the same area as what Moore's law says, Denard's law says that you have roughly the same amount of power in that area. So, if you make the transistor half as big, it'll use half as much power. So we can have a fixed size piece of silicon with a fixed power, and we get twice as many devices, which used to translate into performance. When Denard scaling stopped, and what happened is, again, given what you're studying, this will make sense. But as we made the devices smaller and smaller, we hit a limit whereby when we start thinking about things at the atomic scale, there was not that many atoms between one transistor and the next one, and leakage current, electrons jumping around started being a problem. So the operating power kept going down on the transistors, but the power we lost to leakage current started going up at roughly the same rate, which caused things to change. So if you noticed in 2005, which may be before most of you were studying any of this, because I'm really old, getting older every year, that we went away from making single processors higher clock rate. You could buy a 3.5 gigahertz chip in 2006 or so. You actually can't do that for the most part now, but you buy lots of cores, right? So the other thing is we were running out of steam in sort of architectural designs in how we could arrange transistors to make one processor go faster in the same silicon process. So we just started replicating it and lowering the clock rate, because every time we upped the frequency 10%, we were up in the power 30%. And power is heat, but it also costs money. So when Denard scaling stopped in sort of the mid-aughts, we started seeing the number of cores go up. And I did show this plot a couple of years ago, but it's continued. If you look at what it took to be the fastest machine in the world in 1988, which was 1 gigaflop, there were 8 very high-end vector supercomputing, I think gallium arsenide, in a big cray at the time. But you had 8 processing elements to get to a gigaflop. To hit a teraflop, we got to about 1,000 because, and they were at that point then commodity processors, not big fancy ones. And that was driving some of it. But then core count started exploding as we got to 2008, because we were out of other things to do other than add more processors to first order. So in 2008, it took 150,000 cores to get to a petaflop. This past, 2 years ago, when we hit the first exaflop machine, Frontier has about 9 million processing cores, depending on how you count the GPU cores. The biggest machines known in the world right now, which are not on the top 500 list, which is another issue, but are about 35 million cores that we have out there. So because Denard scaling stopped, that number of cores that we had to put into a big system increased, which means number of chips, et cetera. Even though it's still true that the per square centimeter of silicon, I can keep doubling the number of devices, I just don't get any of the goodness out of that anymore. So so what happened next was, Denard scaling stopped, we started scaling cores instead of frequency. In around 2018, we saw that scaling core counts stopped yielding power improvements. So it used to be in the era where sort of 2006 to 2018, we could keep making the chip bigger, add more cores, but more or less keep a fixed power budget to get performance out of it by just lowering frequency. That ran out of steam about 6 or 7 years ago. And so now doubling the performance means doubling the power. And you can just see that from the chips we bought. So if you look at our Stampede 1 was 2012 when we bought it, 2013 for production. It was 8 cores per Intel Sandy Bridge at the time, the Xeon. Those 8 cores were 130 watts. Fast forward 5 years, 2017, we bought Stampede 2, the Skylakes that I think you run on this week. Those were 24 cores, so the core count tripled, but the power was roughly the same, right? 145 watts. This was when they were saying, we'll never go above 150 watts. By the way, never listen to anything a vendor says, ever. But and then we sort of fell off the cliff. So Frontera was just 2 years later, and with GPUs taking more server market share, and they're like, screw it, we're going to ramp the frequency and to hell with power. So they only went from 24 cores to 28 cores, but they jumped a few hundred megahertz. So we went from 145 watts to 210 watts per cycle, per socket. And those were those liquid cooled nodes you saw yesterday, right? Where we have to pump liquid across them to keep them going. The newest nodes in Stampede 3 that we got this year are 56 cores, so the core count's doubled, but the power pretty much scales with it because they're 350 watts a socket. And the next gen is 450 watts a socket. So, and the GPUs are pushing 1,000 watts per socket. So bigger die. But so we're getting less improvement if you have a fixed power budget. And by the way, power, you have to actually pay for that power, but also you have to build a data center for it, right? And the sort of invariant has been a megawatt computer costs about $10 million. Means that, you know, it used to be that megawatt and your $10 million would double in performance. Now you need a 2 megawatt machine, so that's $20 million to double in performance. So we're sort of flat in dollars per flop more recently. And because most national supercomputing budgets have not continued to double every year, that's a big part of this tailing off that we've seen, is just this fact that to stay on the appearance of a Moore's law curve, where each new chip is higher performance, we've had to ramp up power, we've had to ramp up die size, we've had to ramp up core count, which means we feel less performance, but they're getting steadily more expensive. And in fact, because the core count goes up, and again, we have the high bandwidth memory Sapphire Rapids, but if you put regular DIMMs in those, or the latest AMD chips, or if you look at Granite Rapids or AMD Turin, the next chips coming down the line, we've had to keep scaling out the number of memory channels on the chip as we add more cores, right? Because ideally, you'd like your 56 core chip to have, you know, the same bandwidth per core, right? The same number of instructions you can fetch data to as that 28 core chip, but with a, you know, we have a relatively limited number of pins to get that memory in and out, but we've just had to scale the number of DIMMs you have to buy, right? And in a recent argument with Intel, when I was telling them that their plans are stupid, with where their stock price has been, I can get away with that. It's harder with NVIDIA. Then again, I own stock in both, but I might have made more money in NVIDIA stock than I did in salary last year. But so I don't argue with them that much. But Intel, no problem to explain to them why they're stupid. But you know, when we bought Frontera, it was a $60 million system, right? It has, give or take, 8,000 compute nodes for $60 million. So you can sort of figure out my node price was in the, you know, $6,000 range. For Granite Rapids, where I have to buy 32 pretty expensive memory DIMMs, the memory cost is $9,000, right? Just raw wholesale memory cost. And I'm like, so if I want to buy nodes at $7,000 a piece, and you're going to architect something where I have to buy $9,000 of memory in the node, how much money do you think I'm going to give you out of my total node price, right? So hence Intel stock, it looks like that curve. As a result, but yes, so fixed power and dollar budget means you get less performance in the last few years. And in fact, you know, Frontera, about 40 petaflops. Horizon is about 400 petaflops, but Horizon also is going to cost 2.5 times as much, right? So, and that's just not scalable given the last set of DOE machines was $500 million a piece. And now you see AI investments into the billions, which I could go on and on about, but we'll try not to. So, so there are some reasons this isn't as bad as it looks. And some of them are technical and some of them are totally not. One reason this isn't as bad as it looks, right? I mean, so there's power curves. Frontier and Aurora are the two US machines, one's at Oak Ridge, one's at Argonne, that have cracked an exaflop at this point. And everybody likes to point out, Frontier did it at 22 megawatts with AMD. Aurora with Intel did it at 38.5 megawatts. But if you dig into that, remember these rankings are based on running one code, right? High performance LinPack, solving a linear system. It's been the same code for 35 years. So it's the most tuned and gained code in the history of humanity. right, to make this happen. And so Frontier has these things we've been putting in for AI are little 4x4 matrix instructions. So if you can formulate your algorithm into 4x4 matrices, you get tons of extra performance. And Frontier has those at 64-bit, which you need to run the benchmark. Aurora does not have matrix instructions at 64-bit. And one of the reasons for that is the only code known to man that can use 64-bit matrix instructions to do anything useful is the one that runs the benchmark. I doubt any of you have ever written a 64-bit matrix instruction, and the compilers don't generate it, so I'm sure you haven't. But if you hand code assembly for HPL, you can double the performance. These are used a ton at like 16-bit for AI because they're what's known as tensor cores, and these little 4x4 matrix do your tensor contraction operations in deep learning. So yeah, one's twice the power, but only for that one thing. On any other application, that difference completely disappears, right? So it can be really misleading. The second law of supercomputing is never believe a benchmark you didn't rig yourself. But anyway, and that's just one dimension of performance. As I mentioned, right, with the Stampede 3 processors, by having somewhat static performance per core, we can actually start to optimize the rest of the system and have I/O and memory and other things catch up. So our practical performance is actually improving by more than our peak performance, which means peak tailing off is not necessarily a total disaster. And do I have it in here? Yeah, it's the end of this. The other thing that happened is right about where the slope seems to accelerate around 2017 is when, due to US export control laws, China stopped listing all their systems on the list, right, which took out about 50% of the performance gain. Which is why I said our exascale systems are at 9 million cores, but there's no official mention of the Chinese systems except whenever they submit a paper for, say, the Gordon Bell Prize, and you read a paper about them running on a 35 million core machine, so you know they exist, and I've seen performance data from them, but they stopped putting them on the list. So almost half the decline is the geopolitics of China not wanting the vendors making those to get into the US sanctions. So they stopped saying who's making the big machines officially, because the US decided the top 500 list was a good metric for export control. Related laws. So again, not all disastrous, but still it's a huge shift in the market that we're gonna have to deal with. And so more on that when we talk about AI. Let me say just a couple of quick words about quantum for a couple of minutes. So if you'd asked me any time in the last, I don't know, well, I'm 54. So if you'd asked any time in the last 53 or so years, I would have said that quantum computing is highly uncertain, and we have no idea when it's going to do anything useful. And that, it is possible that we were 3 or 4 years from having useful quantum computing. It was also possible it's fusion power, meaning it's the energy of tomorrow, now and forever. Where it could be 3 years, it could be 30 years, it could be never. Depending on how the device has evolved. So, but I have been persuaded to be less pessimistic about this, partially this week, in talking to Los Alamos people. But a lot of things have happened in the last year or so that makes us begin to believe that we're on a real path to actually useful quantum hardware before the end of the decade, right, in the next 6 years. So, and again, all right, I stole these from Los Alamos. They're not classified. They have nothing to do with weapons, but I still probably shouldn't have stolen them, so don't tell anybody except the 600 of you listening to this online, so it's all over the internet that I stole them. But nonetheless, so perhaps I was at a review this week. So what's happened is, the traditional wisdom on this for the last 5 years has been that, in quantum computing, we're in the area of what they call NISQ machines, noisy intermediate scale quantum. Which means their errors are constant, calibration is really hard, and they're tiny. But they've been scaling up the number of physical qubits, but they make so many mistakes that it's hard to run any real problems on them usefully. So what's happened though is so the long thing was, well, one day we'll have fault tolerance, but they've been able to build some really cool error mitigation circuits that have made huge improvements in reliability. And by at least being able to detect errors that come out of them, you can replicate computation across multiple physical qubits. And they've created the concept, again, all in the last 12 months, of a virtual qubit, where, like with the Microsoft and Quantinuum example here, you have to have a Q in your name if you're a quantum company. They have 30 physical qubits, which is fairly easy to fabricate now, and they've made 4 reliable logical qubits. So you can basically reliably run a bunch of experiments. So they're showing an 800x improvement in error rate, right? So 800x is the kind of improvement they needed to make these things useful, which is why we've been so skeptical about them. This is like a reliable system. And yes, 4 qubits is small, and having to divide by 8 or so from your physical qubits will set things back a bit. But at the same time, you don't need as many qubits in quantum as you do in other things, right? And you probably know more quantum mechanics than I do, but every bit we add, every qubit we add doubles the size of the Hilbert space you can search. So there start to be even useful chemistry problems you could do at like 20 logical qubits. And that's starting to look really realistic. They're out there, and you see this happening, and fault tolerance and errors are improving a ton. If you just look at all the papers in the last 2 years, this is evolving really, really fast. And not just in one kind of computing, but there's all sorts of competing techniques now, right? We have trapped ion qubits, superconducting qubits, photonic qubits, neutral atom qubits. So all of these are improving really quickly right now, and they're figuring out, you see some of these titles, right? Demonstration of logical qubits and repeated error correction with better than physical error rates, right? So, and this ability to make, hundreds of times improvement in error rate really changes everything. So if you look at public roadmaps for a lot of these companies, remember I did say never believe anything a vendor says, but so add 3 years, but the IBM, Inflection, Psyquantum, Q-era, they all have roadmaps that say they will have, there'll be thousands of physical qubits, but the logical qubits is key, right? It will get to enough logical qubits, these virtual qubits, to do something useful in the 28, 29, which means 2030 to 2032 timeframe. And we only need 1 out of those to be successful. And so you see that there's now many billions of dollars flowing into this, and the venture capital money is only wrong about 80% of the time. I will say, so I'm still skeptical, but I'm much less skeptical than I was a year ago about this, because, even if this works, it's going to cover a limited class of problem. And I think Europe's already made big investments in this, but the likely thing to happen is that there will be a limited class accelerator that sits next to a traditional supercomputer to actually do all the work. Part of it is doing the computation you have to do to figure out where all the errors were. But however, quantum chemistry is where they're going to work first to be useful, because the easiest thing for them to do is if you can write a Hamiltonian for a system, model total energy, then it's going to map really naturally into the quantum space, and solves our energy problems and a whole bunch of other things. But they will be somewhat of a bear to program, but so is everything else right now. So you still have to select basis functions and do a discretization and all the stuff we have to do in traditional numerical methods. So it's less, setting coefficients on big polynomials to write a program for them now. So I do think there's a really good chance that, not next year or not 3 years, but 5 or 6 years, we're going to have real quantum chemistry software running on actual quantum hardware at a scale that is useful. And then you'll immediately want 3 bigger scales. So it'll be 2040 before it solves all the systems. But the amount of uncertainty moving into the future around quantum computing has come down an enormous amount in the last 12 months. So just to throw that out there. So, and then let me finish up, try and leave a few minutes for questions. So talk for about 10, 15 minutes about what's going on in AI. And AI was sort of this separate thing, but in the last 5 years, it's almost completely merged with what goes on in high performance computing, right? And so I would argue, and a lot of other people argue it too, but the modern AI, the deep learning era that we're in, right? And there's tons of AI, right? This has nothing to do with random forests or, symbolic logic, or the other AI approaches. But when we talk specifically about deep learning, which in popular imagination has become synonymous with AI, it only exists because of the stuff we've done in HPC over the last 50, 60 years. A lot of it in the open source university community. So one, I took my first neural nets class to try and solve real problems in 1993, and run 9 neurons with a workstation overnight. 2 layers, trivial compared to the problems now. We just were nowhere near the useful computing until about 2012 to go after this. And that's been partially physics, right? The silicon process improvement, partially architecture, things like GPUs, which made a huge difference for this, partially algorithms, right? Fast Fourier transforms, really good linear algebra solvers, mostly linear algebra for deep learning, because in the end, it's all 4x4 matrices at low precision. But so all of that was huge, but what really made it HPC happened in late 2017 into 2018. There was a paper that seemed sort of innocuous at the time, but it came out of Google. It's called Attention is All You Need. You might have heard of it because it proposed the nature of the transformer, which is what all large deep learning systems are now. And by the way, if you feel like you're really behind in AI, almost everything useful in this has been invented in the last 5 years. So it's not possible for you to be more than 5 years behind in AI. So just start reading, you'll catch right up. They reinvent all the words. It's really interesting. More on that in a moment. But attention was actually referring to what was called the attention step in the network. And they said, that's kind of the one that matters for the answers, and all these other things we do like backpropagation aren't that important. And what that did was break all the data dependencies in the software that was keeping us from scaling this stuff up, because that's a sort of embarrassingly parallel problem, is to scale the attention step. So suddenly, instead of here, I have how many GPUs do I pack into my one cute little box on my desktop? It's I have racks and racks of hardware and 9,000 GPUs across servers doing training. And then at that point, I was fairly sure they were going to reinvent all the wheels, but they started using MPI and other stuff from our community, right? Open source, really good implementations of message passing because it was there, and they just, like Microsoft DeepSpeed, totally built on MPI. All the large frameworks are that everybody uses. So all the modern models that you see in the chatbots are all driven by MPI-based codes. But the other impact of this is suddenly the HPC industry is also the $300 billion a year AI industry. And in fact, they've been slowly figuring that out. But you can dig through a bunch of papers now that do analysis on what does it mean to scale a large language model. And it's like, well, we need really fast processors, we need high performance IO, and we need high performance, low latency communication between them. I'm like, yeah, that's kind of what we've been doing since the 60s. So it's exactly what we do in HPC. And if you look at large language models, and I bring this up not only because I think they're useful, but even in your context, large language models are driving how all silicon chips are being built right now. So for your codes, you're going to run on chips that are designed to do large language models because it's inevitable. But they have data parallelism, they have operator parallelism, they have pipeline parallelism. I actually understand for each model that Meta runs, they have 30 people who take that specific model, and their full-time job is to figure out how to adapt it to their architectures. Basically extract the parallelism and find the optimal way to train that one model. 30 people per model, parallel programming training. Not called that, but that's what it is. So again, none of this would have happened without HPC innovations. And some of the good news there is there's a lot that's happened in HPC, and particularly in numerical methods, that has not made it to AI yet, which is going to be incredibly useful when it gets there. So like how to performance tune a large parallel application. Again, Meta hires 30 people per model to do that. There's 600,000 models living in the wild now, so of AIs. So at 30 people per, that's going to be a growth industry. But so performance tuning is huge, but also sparsity, right? I mean, almost everything we do in scientific computing, right, is sparse matrix algorithms one way or another. Sadly, we know how to condition matrices, right? So for us, sparsity means things on the diagonal. We've built data formats and linear algebra libraries and everything to do that. If we have a matrix that's mostly zeros that we want to solve, but has important values down the band in the diagonal, AI is obviously mostly sparse. So these companies spending billions of dollars on GPUs, but Elon Musk said he was buying 300,000 Blackwells 2 weeks ago. I figure that's $14 billion by the time he builds a data center for it. Plus 300 million a year in electricity. But as they spend all that money, it's mostly to compute zeros, which they probably haven't figured out yet, or spending $13 billion on it would be disappointing. But the problem there is their sparsity is random, right? The actual values are not on the diagonal. And I don't think we've figured out how to condition a network that is physically representing a set of neurons. But if you can figure that out, how to do sparse matrix algorithms on something where the values are randomly distributed through the matrix, you will in fact be a billionaire at this point. So, so sparse matrix algorithms are where it's at. So, but the problem with this from an HPC perspective is it's warped everything, right? So HPC traditionally has been like a $10 billion a year industry, which means we're a tiny part of the overall silicon, but we could get a few tweaks to chips out of the main vendors who, for the server chips they needed, we were usually with features they, ahead of the features they need. That doesn't happen anymore. And the biggest issue for us in that is that AI doesn't care at all about double precision performance. In fact, there's now a 4-bit floating point format. I'm not exactly sure how that works. I think they don't have any mantissa. It's just exponent. You just have an implied 1 and a signed bit. I mean, there's even talk of 2-bit and 1.5 bit. But 4 and 8 seem to be the key based on some neuroscience that says your brain works at about 4.6 bits, 22 to 24 levels of voltages that your neurons can distinguish. I don't know why we're spending hundreds of billions of dollars to do something that's no better than a human brain. I got into computers because they were like good at math and reliable, and we've now broken all that and have computers that you have to make them feel better. And well, anyway, therapy later on AI. But so all of our chips, and looking forward, nobody's roadmap, AMD, Intel, NVIDIA, has 64-bit getting any better, right? And so that's another part of driving that curve down. We're gonna have to do crazy things. And again, if you can figure out how to build your codes to do the things you want to model on 4x4 matrices at 32-bit and use those instructions, that is currently 15 times faster than what you get in 64-bit vector. So even if you need more iterations, you need a few 64-bit things at the end to do it. If you can use mixed precision, it's a huge, huge win to do that. And it's going to get worse over time, right? 16-bit, it's 30x faster than 64-bit already. And that's what everybody's paying for. And like I said, what Elon Musk is buying next year is bigger than the traditional HPC industry. There's 75 gigawatts of AI data center under construction right now. That's about as much power as the state of Texas draws in August. So when every air conditioner in the state is running full bore. So with 30 million people, climate impacts aside, there's $300 billion a year in hardware to do that, right? To sustain that. So that's 30x bigger than the HPC market. Every chip is being built for AI at this point. And by AI, I mean deep learning. And by deep learning, I mean large language models. So, so one, we have to figure out how to use that technology in science. But two, we have to figure out how to exploit their hardware in science, which I probably have a slide saying that at some point. But so the good news is there's a certain amount of schadenfreude around this that, we've always worked on fast interconnect, right? You need low latency and high bandwidth to do HPC problems. And we got trashed by the cloud guys for about a decade when they're like, why are you spending all that money on network? You don't need networks, just come to the cloud. We have crappy networks, it's fine. And then AI happened. And they're like, oh crap, we need low latency networks. And we're like, see, we've been telling you this for a decade. Now you're building systems our way. And I enjoyed that for about 15 minutes until the price of the networks we buy quadrupled. Because, so if you saw our data center, a lot of InfiniBand in there, right? All that fiber in the trays over the machines. Across the whole data center, and Stampede 2 was still there with all of its cabling that we've stripped out. You might have seen piles this high of fiber on the floor. But between Frontera and Stampede, we had about 200 miles of InfiniBand cable in there, which sounds like a lot. And by the way, you can't run an InfiniBand cable longer than about 100 meters, right? The protocol doesn't work. So it's not like Ethernet where you have miles and miles of wire. It's a single wire to go between towns. It's only an in-data center technology. Microsoft put in 29,000 miles of InfiniBand last year. Which is, 10x what they made of InfiniBand 5 years ago. So, you know who bought the maker of InfiniBand? NVIDIA. There was a competing product. InfiniBand used to be an open standard. There were several companies in it. Intel bought one, rebranded it as OmniPath. We still have some of that too. But it's just basically another InfiniBand derivative. The same quarter that Mellanox was bought by NVIDIA for $5 billion. And then Microsoft bought like $100 billion worth of it last year. Intel divested itself of the OmniPath acquisition that they had bought and gave it away for nothing. Again, lots of things to learn in that. But yeah, so everything they're buying looks like HPC hardware, which means if you work in HPC, sadly not for me, but you're willing to go to an AI company where, OpenAI, starting senior engineer salaries might be $700,000 right now a year. So it's really good for you. If I'm trying to hire them, it really sucks. But if you need hardware, in the long run, it's good because they're going to build HPC hardware for everything, hundreds of gigawatts per year of it. But if I need to buy it right now and it's in short supply, it's not exactly the ideal situation. So, but in the interest of time, skip a little of this, but I think everybody knows since ChatGPT was released, AI has been, I like to say that's where it jumped from IEEE transactions on distributed systems to like People magazine for articles on AI, right? ChatGPT came out and it became critical for everything. This is just, by the way, about not balanced systems. I mentioned Meta. This is the time their algorithms on their multi-billion dollars of GPUs that they're buying spend waiting for I/O. For their models, which have great names like M1 and M2, because they don't disclose them. So do you think anybody on their infrastructure team has told Mark Zuckerberg that the $10 billion of GPUs he bought spend 57% of their time waiting for I/O and doing nothing? I doubt it. Yeah, again, 30x on the market side. But this means we're going to have to adapt to the marketplace, right? So in HPC, which we've done before. So again, you're all too young to remember this, but in the 80s, the U.S., particularly the defense and intelligence complex, would buy anything that sounded like a supercomputer to subsidize the market for crazy hardware, right? So we had full custom interconnects, gallium arsenides, chip designs, long, crazy vector units. There was tens of companies building them, some of which you've never heard of. Thinking machines, Convex, BBN, SGI. Obviously, Cray was there, and there were two Crays for a while, one of which went away. So, most of those companies didn't survive the end of the Cold War, and the peace dividend meant the government would not drop $200 million on anything you built, whether it worked or not. So at about 1993, unfortunately, I was around for this, Thomas Sterling and Don Becker at NASA Goddard started what became known as the Beowulf Project. Maybe that's a term you've heard, but basically using commodity parts. In fact, what Thomas originally said is that in the scientific computing community, we need to essentially ride the commodity curves. And the quote was, we need to be bottom feeding scum suckers. And these are the words I built my career around. But the gist was full custom silicon, way too expensive for the size market we have. Use commodity stuff, right? And that was the one that I worked on. That was at Clemson University in '93. That was the second Beowulf cluster. And our goal was to get a gigaflop for $50,000. I no longer do gigaflops. We do petaflops and exaflops. We no longer spend 50,000. We spend 150 million. But you know, universities led the way. We dragged DOE and the other agencies sort of kicking and screaming into this. But it was like, we need to buy network switches that everybody else buys. You know, GPUs got started to be used in high performance computing or general purpose computing, you know, built for the gaming market and the graphics market. And this is where NVIDIA got ridiculously lucky, but you know, and it was HPC where they started using, and scientific computing where we started figuring out how to use GPUs and their fast rendering engines to do non-graphics things and general purpose computing. And NVIDIA kept developing that while gaming was floating the company, and then Bitcoin mining was floating the company, and then all the AI codes were built around it. So they went from a company that did, I think 3 years ago, their server sales were in the order of 300 million annually. Last quarter, it was 21 billion. So that's a pretty good 3-year growth rate. But they had gaming and Bitcoin mining to carry them in the interim. So while all the other companies trying to do that went out of business. But we have to do this again, right? What we did in the 90s to transition to commodity clusters, we have to transition to AI hardware to make HPC work, or we're all going to be deeply screwed. And again, AI, if you're not doing AI yet, you probably are. As far as I can tell, everyone under 35 does AI. But again, most of the modern methods have been developed in the last handful of years. And mostly it's the same stuff with new jargon. So now we talk about mixture of experts models, just clusters, retrieval augmented generation, you know, foundation models. Again, little reading, you can catch up on that, but it's the same stuff over again. So mixture of experts, hot topic right now. Build a bunch of small models instead of one huge one because they're cheaper to train, also known as commodity clustering. This is how they parallelize it. That's out of a, you know, sometime in the last 6 months, mixture of experts paper. It also is what sort of a standard parallel processing textbook would have in the 1980s with worse graphics, right? And is there the build in there? Yeah, so they're about to discover that that part's a bottleneck and they have to break it up. And there'll be some fascinating paper that gets 1 million citations about that in the next year or two, because that doesn't scale as your number of experts goes out. And I know that because it didn't scale for doing, you know, all reduce on matrix multiplies 30 years ago. And they're doing the exact same things over again. So, so if you know parallel programming, you know a ton about AI as soon as you make it through the jargon. And yes, we have to deal with power. I mentioned the 15x performance improvement. We also get a very nice gigaflops per watt. The problem with the AI costing this much, I really do promise I'm about to stop, is that the entry point to doing AI research now is about $100 million of hardware, which not everyone has access to, leading to percent of papers in AI from academia, 1960 to 2020. Here's another look. And again, because you have to define what is significant AI research, which is somewhat controversial, but this is 2005 to 2023, another source. I'm looking at this, and I'm an engineer, but the sort of reddish bar there, which means I'm colorblind, is academia papers. So in 2005, it was all academia. And then, you know, Gary Kasparov lost in chess, and you can sort of see the things that happened up to about ChatGPT there in 2021. And the green bar is industry, the purple bar is industry, academia collaborations. Because if you don't have their infrastructure, you've been screwed. And legislatures are just responding to this now with infrastructure investments, Schumer's emergency funding bill, which has no chance, by the way, but still would be nice to spend $38 billion on AI, to have a public infrastructure that would keep up on this. But it is shifted out because of those hardware things. So now, ChatGPT, kind of cute, does interesting things. You can write your homework with it. But how do we use it in science? So I'm stealing this from life sciences, and let me just show you one example of sort of non-standard ways, because yes, we can build new foundation models for predicting materials properties, for instance, right? And there's a ton of work going into that. But right now we have models that understand language, right? So, and by language, I mostly mean English. In fact, they use so much data to train that, like, if you try to train it in Finnish, not enough text has been written in history in that language to train one of these models. But but it turns out you spend a lot of your time reading because there's a lot of knowledge in science that's already out there. So this is an example. Rick Stevens at Argonne did this. Also stolen. I'm good at that. But this took like an hour, the model, once the infrastructure was built. But he said, okay, model, let's take a large language model. Read these 250,000 papers on genomics. So that takes about 30 minutes. I like to refer to these things as sociopathic toddlers that can read at infinite speed. And then it turns out asking it simple questions is not the way to get good answers out of large language models for reasons no one completely understands. But you need to build fairly complex chained queries to make things happen well. So we asked all of these questions in one shot. And he's like, for a particular gene that I care about, CHD4, chromodomain helicase DNA binding protein 4, which 30 minutes before the AI knew nothing about, please tell me, using the knowledge you've been trained on, you have to say that to it, there's so many scary things here, what you know about this human gene and gene product. In particular, I want to know, is it well studied or less studied? What happens with mutations? Is there a drug that targets it? And a whole bunch of questions getting down to what regulates the expression. The bottom paragraph there, if you were starting out as a research oncologist, what is a hypothesis you could explore related to this protein? Basically, what should I write in my R01 grant to NIH? Here's the answer. Again, produced in near real time. So this whole thing took about 40 minutes. It says it's a moderately well-studied gene, and I've annotated it with all the questions that we were asking, right? It's not absolutely essential for survival. It's not directly targeted by any approved drugs. Its mutations and loss are linked to glioblastoma. We asked about cancer links and impacts of mutation. It interacts with HP1A and MTA3. Again, more cancer links. Here's its role in transcriptional regulation. As a research oncologist, an interesting hypothesis to explore could be the investigation of CHD4 as a biomarker or therapeutic agent for glioblastoma and other cancers associated with its loss or mutations. So this isn't a scientific or mathematical analysis. I'll tell you, there's a reasonable chance it's wrong. If you look at how most lab runs, hello, graduate student, please read these 25 papers and come back to me with a hypothesis about what you'd like to work on. And then turn that into lab experiments. That takes weeks. And there's also a fair chance that the graduate student will be wrong, right? So one big use to AI in science is stop treating them like computers where we expect things to be precise and occasionally accurate, right? And start treating them like humans who just work quickly, but are occasionally lie and are wrong. So that's an awful lot of work to get done in 40 minutes. And given that there's tens of millions of papers in the scientific literature, imagine applications in your field from stuff like that. And this is just pulling out of one paper, provide experiments to validate this paper, and it'll generate you a list of experiments where you could validate the results in the paper. So even if we're limited to large language models, just doing English, it's already going to have a remarkable impact in science before we build our foundation models for material properties, right? So please keep that in mind because it's coming faster than you think. I have some examples because I wrote this for some MDs about where it will and won't be useful in medicine. I will just say there's scientific computation where we try and get numerical answers that are right. When you deal with large language models and AI, remember you're talking to a student. So it might be wrong. So you might want to validate what it says before you actually stake your career on it or use it. But you do that all the time anyway. Talk to classified folks and they're like, how do we build classified systems with this? How do we trust it? I'm like, well, I don't know any technical way, but you build classified systems around humans. If we can build it around humans, we can build it around the AIs. So parting shot, theoretically, if you look at the math, all a large language model does is take a sequence of words, which are tokenized. So it takes a sequence of numbers and predicts the most likely next number. And mathematically, that's all it does. Here's a sentence, predict the next word. That seems like simple and that it shouldn't be that complicated. And yet, if you look at that paper example, when you use ChatGPT, you're not talking to the model, because if you talk to the real model, that would be terrifying. So they wrap it around a bunch of mechanisms to not show you what a sociopathic model is. So the internal prompt that GPT would say something like, you're a super smart AI that knows about science. You follow directions and you are always truthful and concise in your response. You have to tell it that or you get a different answer. Imagine that with your differential equation-based code. But anyway, I mean, we all talk to our software, but we don't really expect it to change. So all they do is predict the next word, and yet we have to tell it not to lie. We have to tell it to be helpful. We have to tell it to be concise, what is currently called prompt engineering, but I call it AI therapy. They're amazingly human sometimes, despite the fact that they're built from really simple mechanisms. And what it is the crazy behavior of things at very large scale, just like quantum effects turn into reality as we know it, right? So, and I like to say that as I've learned more about this, I'm not more impressed with AI, I'm steadily less impressed with humans, right? So you think about how kids learn, starts with mimicry. How many people, somebody asks, how you doing? You say fine. It's a learned response. And if you scale it up with enough neurons, you get crazy and complex phenomena at scale. So at TACC, we're here to help you bring scale to your research and see what emerges. So stopping now. Thanks. Time. I know we're over time. Question or two?
Thank you, Dr. Stanzione, for a very nice talk. We'll have time for some questions.
Which one do you want? I feel very cyborg-like at this moment. Yeah. Okay, use this one. You can ask general TACC stuff, programming models, anything you want. Yeah.
So you mentioned that there will be more AI users than HPC users.
Yeah.
Is there any intersection here?
Well, there will be, because I think all scientists will effectively use AI in the next couple of years, but so will non-scientists. So that's why they're going to dominate. So again, something I figured out in the last couple of months, right? You think of ChatGPT as being one giant model, but they really get useful is when you RAG augment them, retrieval augmented generation, or do fine tuning around a particular field. So inside one of the investment banks, I can't remember if it was Morgan Stanley or Goldman Sachs, but they have 3,600 models up and running, all tuned differently, right? So now, 3 years ago they had none. Now they have 3,600 models running all the time, right? Hosting inferences. That's a pretty fast rate of growth, right? Again, there is ChatGPT. There are 600,000 model inferences last time I checked, and this probably is doubling every 2 weeks or something. But 600,000 sort of autonomous transformer models running, learning all the time and doing inferencing in the wild right now. So more than 500,000. It's not hard to envision when we have one of these models for every student as an assistant. They could exceed the number of humans in the not too distant future. Because again, 4 years ago of this kind of model, we had none. Now we have 600,000, right? So I think, yeah, the number of people who use AI, I mean, come on, every time you use your phone, use a map, do a voice prompt, anything, you're using AI one way or another. So the users of AI is going to be in the billions, right? The users of scientific computing doing AI and HPC is going to be in the tens of thousands like it is now, but there's a good 6 order of magnitude gap there. Yes, terrifying. Predict the next word, and now it can tell you, now you have to talk to it about its feelings to get the right answer. So,
Thank you very much for this very nice talk. Going back to the size of funding you mentioned.
mm-hmm.
So we're talking about billions in terms of investment in quantum and AI.
Mhm.
So how do you see this going, in relation to the federal funding we receive for research? So, we are in this kind of field, develop codes. Sooner or later, we're going to compete with this kind of realities outside of academia.
Mhm.
So what's the implication for the current funding model, where basically we are,
Yeah.
a software like ours, instead of one project that supports one proposal or one student, and you set up, 30 people per company, per model developing these elements.
Yeah, and the current non-classified funding for AI proposal on the table in the Senate is $38 billion, right? So roughly one NIH or 5 NSFs. If you like good units for that, I think there's a real danger AI steals all the oxygen in the room, right? So, and even at a curriculum level, I might have told Los Alamos that, just yesterday, that one thing they might want to think about is making curricular investments in universities instead of their usual partnerships to get, we might call a more balanced AI curriculum. Because for what they do, though they desperately need AI skills, traditional numerical methods and computational science are existential, right, for the lab. So if that disappears, that sort of skills, kind of skills you all have, then it's over for them. So yeah, there's some real risks around this, and it is going to squeeze. So like right now, it's a great way for me to easily acquire thousands of GPUs that you can run simulations on. So we have that sort of free rider benefit on it. And again, I think we need to leverage that, but so there might have been an instance at this university, say, where because due to the ridiculous needs for faculty startups in AI training, I went to a dean in the fall and said, I need $2 million to buy enough GPUs for the commitments you're making in these startup packages. And had this been an HPC era question from 7 years ago, I would have asked for 2 million and gotten 1 million. So I asked for 2 million and I got 10 because it's AI. Yes, we have to be very cognizant of how we leverage it because the capabilities, the investments, unlike anything we've virtually ever seen in anything ever, certainly since the dot-com days. But that investment comes at a cost, right, of squeezing out other stuff. So I am worried. NAIR is an example, right? National AI Research Resource, right? Admittedly, I was on the task force and I actually wrote this budget, but the proposed budget is $2.6 billion, and it's led by NSF. What actually happened this year is Congress directed them to start it, do a pilot, spend 30 or 40 million on it with no new funding, right? It became an unfunded mandate. It means that 30 million is coming out of other science budgets. And yeah, so if they tell them to spend 2.6 billion out of NSF's roughly $9 billion budget, and new funding is not coming with it, then it has a huge cost to science. So.
Thank you very much. So two quick questions from Zoom. There is a PhD student from Thailand who is asking if it's possible to run on NSF supercomputer. And then somebody is asking what is the challenge for AI for future generations?
So one of those questions is easier than the other. Foreign collaborators can run on NSF supercomputers if they have a US collaborator to lead the project. Yeah, but it's a public investment in the US, so we prioritize US researchers, but we end up having users all over the world because, of course, teams are global, right, for these things. So, and Thailand's fine, but there are countries on the restricted list that we can't support users from. But but in general, if you're at a US university, regardless of nationality, or you're on a project and there's a USPI, who you're collaborating with, willing to sponsor you, you can get access to the machine. That was the easy question. Worries about AI for the future. So that's a 2-hour talk all by itself. But the short bullet is, I think there's a lot of angst going on right now, some of it actually driven by the industry on like the existential threat of the AIs will take over in Nucus. There's one nutcase that emails me roughly every week about how AIs have traveled back in time with microplastics and are rewriting the future. So you get interesting emails when you run a supercomputing center. But most of those, AI, well, people ask me when AI took over the world, and I'm like, roughly 2014. But because you look at social media feeds, which are AI-driven, and misinformation, and botnets producing it, arguably they've already run the world. Try and get somewhere without the map on your phone and see how much the AIs control you now. But I think most of those existential threats are wildly overblown. The real dangers are much more subtle. And those overblown threats are coming out of the industry to keep Congress busy on crazy stuff and not to focus on the real stuff, like its ability to discriminate against you to get a home loan, which is a very real danger of, we're using data produced by humans, so it's all biased, and those biases come out. It's less of a threat if you're trying to, identify pulsars and telescope images, because not a whole lot of bias to be had there. Yeah, wherever it interacts, I think on the non-science side, where it interacts with society, the ethical risks are fairly large. But it's not going to fire nuclear weapons and Skynet us anytime soon. You can still turn them off, so pretty easily. Yeah, I'm over here in the middle. Yeah.
Is there correlation between the size of computational models that you have?
Historically, yes, but it's changing. And it's a great question, because more data and more parameters, and then more training data to deal with those parameters has been the driver of the field for a lot of years. But algorithms are improving, which means like to get the same quality of answer this year from a language model anyway, it takes about half as much data as it did last year, which was good because they'd already used all the data on the internet, and we're now generating synthetic data from other AIs, which once again shows that there's a lot of people working in AI who've never done science because there's no notion of statistical independence there. But but it does seem like as we get better network architectures and better training techniques, the amount of data we need keeps going down to get the same quality. Now, we still want to drive quality up, so most people are still using more and more data, but there's, again, it's really just been in the last 2 years, but it's awfully encouraging about the fact that improvements in AI models mean the amount of data needed to train them goes down, which means for like scientific foundation models, that's going to have a big impact that we might conceivably have enough data to train them. Yeah. Yeah. Mm-hmm. Yeah, and in fact, in my medicine slide there, I went through it, but you might have read it. I said personalized medicine is the antithesis of deep learning, right? Because you want to do something that's custom tailored to one human, you've now thrown out most of your data set around, say, cancer treatment, right? So, which means mechanistic first principle models matter a lot more in those situations. It's very domain dependent, right? So if you're training it to do math versus English, the amount of data varies. So I don't think there's any universal rules of thumb. There's a lot about, here's my ResNet or ImageNet benchmark, and this is how much data this person used versus this is how much data this person used, and I get the same quality of answer, and that's the name of the game right now in the AI literature. But I'm yet to see, well, there is a law about roughly scaling English interpretation with parameters whose name I forget. But that's what the AI will tell you if you ask it. It'll give you that name. Google will tell you. But no, for like generalized scientific models, we're nowhere close to being able to say, I need this much data. You just sort of throw all you have at it and see if it works or not. Seems to be state of the art. Yeah. Yeah, overtraining does make, you can make the answers worse. Imagine you had a large population that you fed with misinformation for a long period of time. They might make horrible political decisions. AIs do the exact same thing, right? If you overtrain it with data, you can force it down a particular path. You can talk it out of it with what's called few shot learning or